Thank you for your patience with the setup. Veronica plays a little fast and loose with the VGA timing spec, so there's only certain projectors that work. She's very high maintenance. So yeah, my name is Quinn, and I built Veronica, which is a 6502 computer. So the story of this is basically that I'm a software person. I've been programming since I was old enough to climb up on the stool. Started on an Apple II in 1970 or something. And I've always been a software person, but the story of Steve Wozniak having built the Apple II was always just fascinating to me. This idea that this guy who had no formal training in electrical engineering, he just wanted a computer, and so he sat down and built one. And that to me was always magic, and hardware in general has always been magic. So I've had it in the back of my mind, one of these days, I'm just gonna, try to do that myself and see what happens. So 5 years ago, I finally said, I'm going to do it. So I went on eBay and I bought some 6502s to show you how little I knew going into this. I didn't realize Western Design Center still exists and they still make the 6502, so I didn't have to buy some janky ones off eBay, but do so I did, and so that started me on this this odyssey, which seemed like such a good idea at the time. So when you first start out, it's really not that difficult, right? You take, so obviously I'm preaching to the choir here, you're mostly hardware people, but for us software people, this was all news. So yeah, I mean, you get a breadboard, you stick the CPU on it, you clock, I made a little display there, a little bit of RAM, and right away, you can step through code, watch it change memory, and that took, a few weeks, and I thought, wow, this is amazing. I'm awesome. I've almost got this thing going. So start thinking, I'll get some graphics going. Maybe do a GUI. I'll do a little bit of maybe a game or two. I'll do some operating system stuff. It's going to be great. Yeah. So 4 years later, I had it hello worlding, and turns out hello world is a lot harder to write when you have to build the computer first. The theme of this project is that, am I needing to speak into the mic? All right. Oh, well, there I am. So the theme of this project is sort of that I didn't know enough to know what I didn't know. And it's kind of a good thing, because I honestly wouldn't have started it if I'd known how challenging some of this stuff actually is. So, I mean, it took me 5 years to get to this point, and it was a lot of this. It was my desk covered in crap. In that shot, you can see my breadboard, you can see the machine, you can see my laptop, you can see the Flash programmer for Atmel, the oscilloscope course. So I would make a little progress and get stuck on something, realize I didn't know what the hell I was doing, and then spend 3 months Googling and reading and Googling and trying to figure out how these things actually work, and then make a little progress and keep going. So that was the story of all this. So the theme here is that don't let not knowing how to do something stop you from doing it, because you really can figure anything out if you just keep at it. So just keep at it and keep at it. So the basic design of the machine is, it's a backplane design, so there's just a backplane on the bottom with everything as a card stuck into it. And that turned out to be a good decision, because it allowed me to build small pieces that could be added to it bit by bit, and each of these pieces could be tested, independently. Really the same model you'd use for building a complex software system, right? You just, you sort of unit test, if you like. So that was the process. So I'd have an idea, okay, this is something first I need to, I think in this shot here is the RAM, I believe. So pick a next component that needs to be built, and throw it on the breadboard, get it up and running. Well, maybe sketch it out on paper or whatever, how I think it needs to be built. Put it on the breadboard. Of course, it doesn't work. So then there's a lot of this. You can tell how well it's going, I figure, by how many probes your breadboard has sprouted. So this was not going well, as you can see. So there'd be a lot of that, and then there'd be a lot of this. And this would be the part where I'd start Googling and figure out what the hell went wrong. And once I had it kind of working on the breadboard, then from there, I'd go to sort of integrating it into the existing system. I didn't make a lot of good decisions on this thing, but one of the few good ones I did make is that the backplane, which you can see under the cards there, has a breakout at the end of it, so I can prototype something on the breadboard and kind of patch it into the existing system and kind of get the integration portion of it going, because there's different levels of bugs at each step, right? So you've got design bugs, things that didn't work in the schematic, and then you've got physical things that don't work once you get it on the breadboard, and then there's systems level problems where you get it connected to the machine and it doesn't work because of some timing issue or some conflict with another board, or this sort of thing. So once I had it working at kind of this stage, then it was time to sort of get busy. So then I'd build it in Eagle, and each of the boards is the maximum size permitted by the Eagle free version, which is turns out to be kind of a good size actually to work with on this scale, but it did control a lot of decisions. So there's I think 6 boards in here, which there's a lot of boards for how little it actually does, but it's because I ran out of space big time. The VGA board was tough to fit. So I draw it in Eagle, and then it was a fun excuse to learn PCB etching, so did the whole etching process. I would lay it out in Eagle, and this was an example of where I'd never done anything like this before, and turned out to really enjoy PCB layout. That's a lot of fun, especially when you're trying to do a single layer board so that you can etch it yourself. It's a real fun kind of puzzle to rearrange things. It's like those puzzles where you've got all of the dots connected by lines, and you got to move the points so that none of the lines cross. You remember those? Yeah, anyway, I really enjoyed that. So the process I've seen, which you may recognize from such blogs as Hackaday, is to take those Eagle files and print transparencies, and then I use the pre-sensitized boards and just expose them under my desk lamp. This whole process, each of these boards is built for like $1.50. That was sort of key to my process. And mostly you see online people doing the wet paper towel clothing iron business. I don't know what that's about. I don't know why people don't use these pre-sensitized boards. It's by far the easiest way, I think. But so the process I use for etching is vinegar and salt and peroxide, which I found online somewhere, and it works great, and there's no nasty chemicals. I etched all these boards in my kitchen, and you can practically eat the substance that you're etching the boards in. Not that I would recommend that, but so then just drill and place the jumpers and build a board and test it. So that's sort of the process I went through for each board as we went along. And obviously I'm cramming a 1-hour talk into 20 minutes here, so I'm glossing over tremendous amounts of detail, but what I'm hoping to do is kind of have some time to take some questions. Obviously, all the gory details of this are on my blog, so feel free to scan that at your leisure. The first 20 people are going to get rickrolled, fair warning. I guess at the end of the day, so where the machine is now is, let me see, we got her hooked up. So that is basically, that's just demoing the VGA generator. That image is hard coded in ROM, so it's just copying that into video memory. There's 64K of system RAM, 4K of ROM, and 64K of video RAM. It's 256 by 240 resolution. It's 8-bit color, 2 bits per component, and then 2 bits that I threw away because memory's cheap. And so the video generator is actually one of the worst decisions I made on the project. So I opted to do VGA because A, I didn't know any better, and B, most homebrew computers use composite video, which is really easy to generate. But I actually don't have anything in my house that would display a composite signal. Seriously, like I checked, and my TV has 14 HDMI ports on it, and so it was clear I wanted to be able to build something that I could take to a group like this and be able to plug it in and have some hope of showing people stuff. So composite was kind of out. So that meant VGA was kind of the minimum standard that I felt you still have any hope of finding. And even that, my TV doesn't have it anymore, but my monitors still do. So I wasn't going to do HDMI, so it was going to be VGA. And VGA is fairly simple to generate. The problem is you do need a fair amount of horsepower to generate it. There's a lot of pixel data, and the clock speed's fairly high. So the machine runs at 1 megahertz. The video card runs at 20, and the The other decision I made in hindsight, which was stupid, was to bit bang the VGA signal from an Atmega 368. I did that because I'm a software person, and when your only tool is a hammer, you tend to treat every problem like a nail. So I threw software at everything I didn't know how to solve. And so I thought, well, if I can just get an Atmel microcontroller running fast enough, I can just do this all in software. And I understand software, so I'll do that. And now I know why they say don't ever send a microcontroller in to do an FPGA's job, because it really should have been an FPGA that did this. But long story short, so all of the video sync timing signals and pixel data and everything, pixel clock and all that is all just being jammed out of the I/O ports on an Atmega. And that's why it mostly works. There are some monitors that don't like it, and I've never really figured out why. And the picture is also a little dim, and I've never figured out why. In theory, everything is in spec, but that's the real world of video standards. So that represents about 3 years of work right there. So everybody always oohs and ahs at the case, but if you want to make me feel better, ooh and ah at that, because see, that's why this is a thrill for me, because I can bring this thing to here and have a room full of people that I don't have to explain this to. You just get it. Like everyone else, all of my normal friends look at this and I have to explain why. Why would you spend 5 years building that? It doesn't really do anything. So you guys just get it. So that's awesome. All right, so let's show a little something else. All right, there we go. All right, so it doesn't actually have any software, but there's a little bit going on in ROM there. There's you can examine and modify memory. You can jump to memory. So my goal was to build a computer, and that's easy to say, but computer has a lot of definitions, right? So my definition of computer was something that could be used to write code for itself on itself. All right, so I had to be able to turn it on and type in code and run it on the machine entirely. So you can do that just barely with this. There's no assembler, so you have to hand assemble it, but you can, using various ROM monitor commands, which I won't bore you with, you can, yeah, write code into memory and run it, and it will work. So, and then, let's see, and then I had some, oh wow, this is hard upside down. And then I had some ROM left over, so, sorry, it's case sensitive because that was less work to write. There we go. And so I put Pong in ROM because why not? So 80s computers mostly had BASIC and ROM, but I thought Pong and ROM was much more fun. So, so maybe I'll set this up over there at some point and people can play Pong. But honestly, it was productive because I needed to test the VGA system. The video generator has a sprite system in it, so and a font generator. So I needed to, the score is rendered by the font generator, and then the paddles and everything, the ball are all generated by the sprite generator. So it was kind of a way to test all that. So I have no idea how I'm doing on time, but maybe I can take some questions. Okay, perfect. So, anyone? So the tool chain, actually I took I have a whole set of slides on the tool chain, which I took out because that adds 30 minutes to the talk. But the tool chain is all built on CC65. So I modified CC65 to generate code that would match the memory map in this. And so the ROM, the ROM board has an onboard EEPROM programmer. So there's an Atmel on that. I was saying to some people earlier, there's a 6502 in here, and it's ostensibly a 6502 computer, but there's like 6 Atmel chips in it. So it's debatable who's doing more work. But one of those chips, one of the AVRs, is acting as an EEPROM programmer, so I can plug in my laptop and I can compile code in CC65 and then dump it through, a normal AVR programmer into the ROM board, which then flashes it onto the system ROM. So that was because EEPROM programmers are expensive and I'm cheap. So a couple of shift registers, you can build an EEPROM programmer. So that's the basics of the tool chain. And then similarly for the video generator, there's obviously an Atmel in there, so there's another connector on the back here for programming that. And that was all done in like AVR GCC and AVR Dude to flash it. So. Yeah, so I guess that was an easy choice. I mean, I adore the 68,000. That's probably my favorite chip, but it's definitely an order of magnitude more difficult to build a computer off of for your first time. There's a lot more address and data lines and all that, so especially with limited board space that I had, I thought I should probably stick to something 8-bit. I considered the 6808 as well, which is kind of a neat compromise, 68008. But yeah, the 6502, I mean, it's the first chip I learned to program assembly in, and it was the chip in the Apple II, and you know, virtually everything else in the 80s, so it just seemed like a logical choice. And it's honestly a super easy chip to get up and running. Like literally that breadboard I showed earlier, I mean, you know, anybody can do that in 10 minutes. I mean, it's so easy, a software engineer can do it. So it's a great chip to learn this sort of process of building computers.
Two questions. How long did it take from starting to what you considered successful for what your original goal was? And what was the first code that you ran out of, just like in addition or something?
Yeah, so I generally quote the number 5 years. And I only know that because I looked at my own blog, which you can scan right there. I had to go back and look at the dates on the blog posts to know when I actually started, but that picture I showed of the 6502s on the foam that I bought from eBay, that was taken in 2009. So, and then I got to this point like this year at some point, a few months ago. So I sort of say 5 years. First code I ran on it, boy, it's sort of a gray area because, well, I guess technically the first code I ran out of was the free run, right? So the first thing you do with a 6502 is you hardwire the data lines to the hex value EA, because that's an op, right? So it's a neat trick to sort of get the CPU running from scratch, because no matter what it reads, it will get EA. So it's going to, when the chip starts up, it pulls it pulls an address from the reset vector and jumps to that point, and then starts pulling code from that and executing it. So it'll pull an EA, it'll jump to EA, and then start pulling EAs. So it'll just execute NOPs forever, basically. So that, I guess, is technically the first code, but yeah, I mean, the first code in the video generator, which is frankly arguably a second computer that I had to build first to put in this computer, was, I'm sure, just rendering a white pixel in the upper left or something. I don't know. Thank you. Other questions? Yeah. Is the question what input interfaces are there? So there's a USB keyboard and 2 Nintendo gamepads. Nintendo gamepads are on there because I wanted something a little bit fun. I knew I wanted to make a couple of games. Turned out to be a game. And also the Nintendo connector is called the D-Cannon, so how could I not use it? That's the best name for a connector ever. And if you look at it, you're like, oh yeah, it's a D-Cannon. They're also, yeah, they're literally a shift register in a plastic box, so they're quite fun to interface with. The keyboard, again, that was another case of, so I think of Veronica as, I wanted to build an 80s computer, but the problem with that is that computers from the 80s all still work perfectly well, right? What failed is all the stuff around them. The disk drives, the keyboards, the monitors have all failed in the intervening years. So I kind of had the same problem. If I'm going to build a new 80s computer, I needed to have it interface with modern equipment, and that's really the hardest part, is because we throw so much performance away at stupid stuff nowadays. You know, USB takes a lot of horsepower to run, but we don't care because horsepower is cheap now. So I had to kind of wrap Veronica in an 80s bubble. So the 6502 thinks it's in 1981, but there's all these AVRs in a cloud around it, translating the modern world into 1 megahertz and 8 bits. So the keyboard's a great example of that. I wanted to do a USB keyboard because that's what you can buy now. This keyboard was $3 on Amazon. Thank you, globalization. And but USB is actually quite difficult to deal with. So it's actually cheating. I've discovered that basically every USB keyboard in the market is all using the same USB interface chip, probably made by some factory in China, and that chip has a PS2 compatibility mode in it. When the keyboard boots up, it sends some bits to the host, and depending on what it gets back, it decides whether to boot into USB mode or PS2 mode. And so that was easy enough to trick the keyboard into running in PS2 mode, and PS2 is quite easy to interface with. So it's a PS2 keyboard through a USB port. So it's cheating, I guess, but it achieves the goal, which is I wanted to be able to buy a modern keyboard off the shelf, plug it in, and have it work. So there's a USB port on the front, which is sort of a keyboard-only port, if you will. So that's it for input. The big thing missing is mass storage. It needs like an SD card or something like that. There's no mass storage. So the only thing it can do right now is run code out of ROM. So, yeah.
Over the 5 years, how stable has the breadboarding been?
How stable has the breadboarding been?
You have to go back and redo the wire and fix that.
So yeah. So the PCBs is part of the reason I wanted to etch PCBs and not do something else, because I wanted something that was going to be fairly robust. And yeah, it's held up great. Everything still works that I built originally. The power supply is actually the first PCB I ever etched, and it is terrible. But it still works somehow. I mean, the traces are way too thin, and there's like green oxidation all over them, and I can't. But it still works. I don't know how. So yeah, that's fairly robust. A couple of the boards have been rebuilt because I screwed stuff up or whatever, and had to make enough changes. I mean, the boards all have jumpers hacked all over them because I would realize I'd made mistakes or whatever, and didn't want to re-etch the board. So yeah, I mean, I knew I was going to want to take it to shows and stuff, so it's fairly robust in there. I'll open up the back later so people can come up and see it. Things are clamped in down there, and everything's screwed in, and so yeah, I recently took it to a show in Kansas City, and it rode with me through 4 airports and survived. So I guess I did something right. Other questions? Yes.
Your debugging process seems mythical. The ability to figure out what's going on. Did you develop all those skills for this project, or did you already have them?
No, I guess that came from software. So my day job is these days writing mobile apps, but I spent 20 years in game development, and game consoles, you're always coding on the latest and greatest hardware. So it's stuff that is not out yet or just came out, and so the tools are always bad, and nothing's documented, and modern game engines are really parallel, and you're doing a lot of stuff on the GPU and different CPUs and vector processors, so you spend a lot of time debugging hard problems, and I guess that's where it comes from. I mean, trying to debug a race condition in an undocumented vector unit that you can't halt and has no output that you can render, so it is difficult. So you get very good at eliminating variables and just doing things with trial and error. So I guess that's where it comes from. I mean, the one sort of good tool that I did invest in is I eBayed like a 10-year-old mixed signal scope with a logic analyzer, and there was a couple of problems where that saved me. A couple of issues with the VGA generator I could not have solved without a proper logic analyzer. So yeah, there is still a place for good tools, but mostly I debugged it with sheer force of will and trial and error and eliminating. I mean, you can do a lot with blinking an LED. I debugged the entire EEPROM programmer with blinking an LED because it's like, okay, well, you step through the code, so you say, okay, well, turn the LED on here and off here, and now I know if it executed this code or that code, and you see where the branches are going, and I know you can check the contents of a variable at any point by checking, is it this value, turn the LED on. If it's this value, turn the LED on, and it's slow, but it works. So it was either that or invest in like JTAG debuggers and all that, and so see earlier, cheap. Other questions? No? All right. I guess that's it.